In fact, in the field of automobile consumption, the deep substitution of electric cars for gasoline cars has already begun, which is on a large scale and develops rapidly. It has a far-reaching impact. Ningda in Fujian province is the world's largest electric car battery production base. A quarter of the world's electric vehicle batteries are produced here. An average of 1,000 batteries are rolled off the production line every minute. Wang Shengwei is an electric vehicle power battery engineer. He and his team have been working towards a goal to increase the energy density of the battery. This is a key in determining the drive range of an electric vehicle. In the past 10 years, Wang Shengwei's team has tripled the density of battery packs by developing chemical materials, reaching up to 180 watt-hour per kilogram. Increase the cruising range of electric cars from less than 200 kilometers to more than 700 kilometers. This is close to the limit of battery energy density without a major technological breakthrough in chemical materials. However, Wang Shengwei's team did not stop here. This time they tried to break through structurally in design. Ordinary battery packs consist of modules. Each module contains about 10 cells. Wang Shengwei's plan is to remove the module structure and directly integrate the cells into the battery pack. The same battery pack space can fit more cells. As a result, the energy density can be increased by another 20%. However, there are more than 100 layers inside each cell. If the thickness deviation of each layer is 1 micron, the average thickness deviation of the cell will exceed 0.1 millimeters. If the number of cells in a row is between 20 and 30, there will be a cumulative deviation of 2 to 3 millimeters. This will prevent the battery pack from being assembled. Such structural changes impose an extremely high requirement on the consistency of the cells.
When mass production products is near to being delivered, due to large amounts of cells, at that time it is quite difficult to achieve a very good control on consistency of cell layers error.
The key to controlling battery consistency lies in these slurries. Slurry is a paste that carries the positive and negative electrode materials of the cell. The requirements for the slurry are good flow performance, stable viscosity, and no solid sedimentation. In order to achieve these goals, Wang Shengwei and his team used a year of trial and error to get the ideal formula. The mixing of graphite, binder, conductive agent and water in specific proportions is a secret technique of the team. They are fully stirred in an automatic negative pressure tank and will be applied to the copper foil after mixing well. The production process strictly controls the average thickness deviation within 0.1 millimeters for a thickness of 60 millimeters of cells. Finally, they achieved a standard of overall quality improvement. The idea of directly integrating the cells into the battery pack was finally accomplished. The battery energy density is increased to 220 watt-hours per kilogram, which will increase the cruising range of electric vehicles to more than 1,000 kilometers. For Wang Shengwei, achieving this goal is far from enough. 15 years ago, he had researched and developed mobile phone batteries, which created a legend of 5-minute fast charging that lasted the phone for 2 hours talking. 5 years later, he changed his career to electric vehicle battery development, and he hopes to bring the convenience of fast charging to electric vehicle users. However, a single electric vehicle power battery is 10 times larger than a mobile phone battery and has 3 times longer life. There are 20 times more cells in the battery pack. Technical challenges are even greater.
From the user's point of view, people hope that the charging of a car can be just as quick as filling up a gas tank of a car. This is ideal. Our current first step is to achieve a 15-minute fast charging.
The team led by Wang Shengwei is racing against time. The super idea of fast charging depends on whether they can make improvements to the material structure that will speed up the lithium ions moving.
Using synthetic graphite is common. We found it to have a downside. Its fast charging capability is relatively poor. But its advantage is that the energy density is relatively high.
We transplanted the surface properties of natural graphite to the synthetic graphite. This achieves a faster charging, and also a longer life cycle.
Wang Shengwei's plan is to use a supercraft process to form fast ion rings on the surface of synthetic graphite, creating a microscopic industrial world. The fast ion ring greatly reduces the transfer resistance of charges and provides more transmission paths. Thus, they achieved a substantial increase in the rate of lithium-ion intercalation per unit time. Whether the battery made of the improved synthetic graphite can really enter mass production must undergo a charging test under normal temperature conditions of 25 degrees Celsius. The test begins. How much can the new solution shorten the charging time? In less than 12 minutes, the battery was 80% charged.
At 100%, the test is complete.
This means that a battery pack composed of such cells can provide a car with a driving range of 400 kilometers after just 15 minutes of charging. Only a year ago, such charging speeds were considered impossible. Such higher energy density and faster rechargeable batteries will make electric cars more convenient and efficient. In the field of charging equipment, Chinese engineers are also racing against time to improve technology and make charging faster. In Qingdao of Shandong, Dijang Yu led the technical team to test a new generation of super-fast charging equipment.
Are the load parameters set? Connect the load and prepare to charge. Start charging.
As the voltage and current increase, the charging power begins to climb continuously. After 3 minutes, the charging power is close to the peak of 320 kilowatts. In the design of this high-power charger, the Yu Dexiang team adopted a new liquid cooling system. Compared with air cooling, the cooling is more effective.
Over time, the higher the temperature, the higher the circulation rate of its liquid cooling. It will take the heat out. This ensures the safety of charging.
The entire runtime is 20 minutes. The temperature rise is still within the normal range, and has tended to stabilize.
The new generation of supercharging equipment successfully passed the test. This means that charging with new equipment for less than 10 minutes an electric vehicle can travel for 400 kilometers. Such a charging speed is close to the experience of filling up a gas tank. The rapid upgrade of battery and charging technology will greatly accelerate the popularization of electric vehicles. However, a new challenge will follow. A random disordered charging at charging poles cannot meet the needs of large-scale electric vehicle development. For example, if 100 vehicles return to a residential area at roughly the same time and use charging poles for disorderly charging, the electrical system could be overloaded. Yu Dexiang's team's plan is to replace traditional charging poles with charging networks, so as to achieve orderly charging. All charging terminals in a planned area are connected to energy source management devices to the utility plant. The system manages the charging sequence of the car according to the real-time electricity load of the plant, in order to avoid the impact of concentrated charging on the power grid.
The charging pole actually uses a physical plug to charge the battery of a car. As plugged in, it is being charged. But on the charging network, when it is actually being charged is uncertain. We will charge and discharge a car in an orderly manner according to the needs of the tenants, as well as how much remaining battery power of the car, and the surplus power in the grid at any given moment of time.
In the past 6 years, Yu Dexiang's team has replicated and promoted this plan, and has built a map covering more than 350 cities across the country. A charging network with more than 332,000 charging terminals. Not only that, in this new industrial Internet of data link and energy interaction, they have also added real-time monitoring and big data analysis technology to conduct full examination of each battery during the charging process, which the collected charging data to be pushed to the central platform in real time compared with the historical big data for analysis and comparison. If a safety hazard is found, the charging is stopped immediately. This ensures charging safety. This is considered as one of the ideal charging solutions to meet the large-scale use of electric vehicles in the future. The dream of Yu Dexiang is to provide more comprehensive energy-saving solutions for owners of electric vehicles.
Each electric car only needs about 50 to 180 kilowatts-hour of electricity. Running for 50 kilometers only needs 10 kilowatts-hour of electricity. 70% of electricity is unused in most cases. Precisely, we can use 70% of the electricity to achieve coordinated dispatch with the power grid and between energy utility sources. That helps the power grid balance distribution to ease the peak hour and fill the off-peak hour, making the power grid far safer.
Can Yu Dexiang's dream come true? It's crucial that they perform a test today. The 36 electric vehicles and charging terminals participating in the test have all been upgraded with the V2G technology. This means that these electric vehicles can either be charged through a charging device or discharged in reverse that releases electricity back to the power grid, which we may call an electricity bank.
The charging of 36 vehicles is now started.
The test begins.
The total power reached 979 kilowatts.
Yu Dexiang's goal today is to have 36 electric vehicles that originally only have charging needs then discharge reversely to the local grid at the same time. This is a very bold attempt.
Immediately go to discharge mode.
A successful test means EV owners can charge the car when the grid is plentiful, and discharge to give electricity back when the grid is strained. While enjoying the convenience of travel, you can also enjoy the benefits of energy sharing.
As an ordinary user, driving a gasoline car costs money. But driving an electric car has the potential to make money. Fully charging your car at home may cost you 30 cents. During peak hour electricity prices then may be as high as 1 yuan and 20 cents. You can discharge the car's electricity and sell it to the grid for profit.
Not only that, but this technology also links the charging grid to the energy grid.
If there are 3.6 million vehicles in the country participating in the off-peak hour charging, it will be a huge contribution to balancing the power grid and ensuring the safety of the power grid.
At this time, 36 electric vehicles continued to discharge, which has reduced the instantaneous power load from 538 kilowatts to 89 kilowatts on the grid. Nearly 80% of the load power is provided by these electric vehicle discharges. The AI camera uses technologies such as image recognition and infrared temperature measurement to monitor the equipment participating in the test in real time.
Now, the discharge power has reached 401 kilowatts. Peak shaving can account for more than 30% of the total load.
The test passed. In Yu Dexiang's mind, the future scene of the electric age is gradually approaching us. In the near future, the large-scale development of electric vehicles will form a huge mobile energy storage network through the link of the charging network. China is accelerating its efforts to achieve carbon neutrality. However, this will only be possible with robust and smart super grids providing power delivery. The manufacture of a single solar cell can be traced back here. The pipes that the workers are overhauling look no different from the outside, but there are violent reactions on the inside. The silicon powder extracted from the ore is chemically processed to obtain trichlorosilane. Workers are purifying it. Rectification is to separate impurities in trichlorosilane by heating according to different boiling points. It's all about making higher purity silicon, because silicon is the most important material for solar panels. Luo Zhouyu, a senior technician, uses purified trichlorosilane to produce silicon. The purity of silicon directly affects the power generation efficiency of the panel. The higher the purity of silicon, the higher the requirements for air cleanliness in the process. Therefore, before entering the revivification building, workers must remove the dust adhering to the clothes through an air shower system. In the 2,500 square meter revivification building, 27 revivification furnaces are opened every 4 hours. Opening the furnace means the manufacture of millions of dollars worth of high-purity silicon is complete. Silicon cores with a diameter of 10 mm were sequentially mounted on electrodes at the bottom of the furnace. The reacted high-purity silicon will grow on its outer surface. After the furnace is closed, energized and heated, the temperature inside the furnace is stable between 1000 and 1080 degrees Celsius. Gaseous trichlorosilane and high-purity hydrogen are injected into the furnace. The diameter of the silicon rod increases by 1.7 mm every hour. The entire reaction process takes more than 100 hours. At this time, the silicon core of another furnace has been transformed. When the furnace drum is lifted, the diameter of the silicon rod at this time increases by 16 centimeters, the weight increases by 125 kilograms, and the value is increased by 100 times. In order to prevent pollution, technicians first use vacuum equipment to remove the impurities on the bottom of the revivification furnace. Next, the workers have to cooperate with the robot arms to remove the silicon holder as soon as possible. The silicon rods from each furnace must be tested for purity. In the testing center, the number of dust with extremely small particle size is controlled within 1,000 particles per cubic meter. Higher cleanliness ensures accurate test results.
Well, this batch is of good quality.
The purity of this batch is as high as 11 nines.
The higher the purity of the silicon material, the higher the photoelectric conversion efficiency of the cell.
However, from silicon material to a photovoltaic cell that can actually be used to generate electricity must undergo many manufacture processes. The processes of single crystal silicon pulling rod and silicon wafer cutting are often carried out in different factories. What this factory has to do is an important step, which will turn silicon wafers into cells. Today, engineer Wang Shoupeng is going to upgrade the production line that has been running continuously for only 130 days. It only needs to add 3 more processes to the original production line, which will increase the photoelectric conversion efficiency of the cells by another 1.5%. In the photovoltaic cell industry, jogging is a step backwards. You have to run. The ultimate pursuit of efficiency results in the iteration of products and technologies becoming very fast. The 60 technicians in the night shift had to cooperate with him to complete the final equipment testing and adjusting. The new production line is up and running. Wang Shoupeng and his colleagues waited anxiously. The first batch of brand new cells just came out. The new technology has been applied. The coating material on the reverse side of the battery sheet separates the silver electrode of the battery from the cinnamon sheet. Then, the photoelectric conversion efficiency of the battery is further improved. The upgraded cells have a photoelectric conversion efficiency of up to 24%. This is a new world record. This new production line can produce more than 50.4 million cells per year. If all cells are installed, it can generate about 450 million kilowatt-hour of electricity every year. Just over a decade ago, China was unable to produce a high-purity polysilicon on its own. Manufactured photovoltaic cells are also mainly exported for use abroad. Today, a complete industrial chain allows China to have the world's largest production capacity of photovoltaic cells. Not only that, today China's total installed photovoltaic capacity ranks first in the world. Power generation ranks number 1-2 in the world. In the field of photovoltaic power generation, China once again leads the world.